In this video, I want to talk about analyzing fluid flow, and we'll go through these different steps. Actually, in this video, we'll probably just concentrate on the middle ones, but the overall procedure is going to be to start with a conceptual model that outlines the problem you want to solve, and then identify governing equations and boundary conditions that are consistent with the conceptual model. We'll need some fluid properties, and then we can go and take a look at examples. So this is what we'll do in the course. What I want to talk about right now is how we go about getting the governing equations and boundary conditions for fluid flow. And in particular, I want to take a look at how we get the forms that of these equations that are used in Comsol. Okay, so we're going to have two unknowns, the velocity and the pressure. And for that, we're going to need two governing equations. And we'll use conservation of mass and conservation of momentum to guide us in the development of those governing equations. So we can start with the general conservation equation that I show here, the divergence of the flux plus the rate of change of storage of this quantity C is equal to a source term there. So this is the statement of the general conservation equation, and we talked about that earlier, so we're just going to assume that that's okay and that'll suffice as a starting point. So here's that starting point, and this term here, cap gamma, is the flux, and we're going to consider two possible fluxes, the diffusive flux and the advective flux. Now, for conservation of mass, we're going to start with this cap theta term, which would be mass, and that is part of the procedure that we've been using previously in the class, and then we'll use that then to define lowercase c, and that's going to be cap theta per volume, and so in this case that will be mass per volume, and this is going to be the total volume within a little infinitesimal block in the control volume. Okay, so that's total in units of total volume, and this is going to be a continuous fluid, so the mass per unit volume will be the density of the fluid. So that allows us then to start looking at these individual terms, and the first one that we'll do is the storage term. So dc dt, I mean, this is pretty straightforward. C is identified as the fluid density, so we just get the rate of change of the fluid density with time. Now, the advective flux, this is going to be, in general, a volumetric flux of the fluid times C, and the volumetric flux is going to be the volume of the fluid per area total per time. That'll be the units of Q. And for a fluid that's just a continuous fluid, the volume of the fluid and the total volume are the same. So this ends up having just units of length per time. And we can just also use that as equivalent to the average velocity. And so the advective term we also can write like this, where we substitute in the density for C. And in this case, where we're doing conservation of mass, The diffusion term is just going to be 0. And it's possible to have a source. We could have a source of fluid. Maybe if we're injecting fluid, that might be, we could treat it as a source. That would be a potential approach. So we can include that. We'll just call this M, and that would be a mass source where it's got units of mass rate per unit volume. It may be, I mean, we're including it here just to keep things general. In a lot of cases, we're just going to set that equal to 0. Okay, so we can substitute in and these terms going into this general equation, and we've got the divergence of the flux. It's just the advective flux, which we have right here. So that's the divergence of the flux there, and then we add to that the storage term, which is this, and then we have the source, which we're just calling cap M. Okay, so that's the conservation of mass. Now, conservation of momentum will take a similar approach. That we're going to use this as the starting point, except now the thing that we're going to conserve is momentum, which is mass times velocity, and then little c, and following convention, will be cap theta per unit volume, and that's going to be equal to mass per unit volume times velocity, and that's just going to equal density times velocity. So that'll be c, and we can then just jump right to the storage term, which is that. And this is, in general, we're assuming that the density and the velocity could both be changing with time. And for the advection, we go back and say, well, okay, what we saw last time was just Q times C for the advection. This is the movement of the quantity that we're conserving with a flowing fluid. In this case, we saw last time that the flux, the volumetric flux, was going to be equal to the velocity. And so we can do that times c, but then we also have c up here, so that ends up giving us, let's call it that, the density times the velocity times the velocity. And so this is a bit of a peculiar thing. This is the product of these two vectors, a dyad, times the density. So that'll be what we'll use to describe the advective flux. So the diffusion of momentum we can think of like this. Mass times velocity, there's momentum, and this is going through a unit of area. And there's area. So the flux through that area is going to be the rate of change of the mass times the velocity per unit area. So that's a way of thinking about the momentum flux. And we can take a look at the units of that, and that's going to be, let's see, the area is length squared, mass and velocity is length over time, and then there's another time there. So that gives us basic units of mass over length times squared. So that has the same units as stress or pressure. So stress and has the same units as pressure, and that has units of a force and a pressure, or a stress and a pressure is a force per unit area. force is mass times acceleration per area. So that's mass length times square, that's acceleration. There's the area, and that gives us mass length times squared. Okay, so this momentum flux has the same units as stress. And to see how that works, this kind of on an intuitive basis, I think it's useful to look at it like this. So here's the cross-sectional area, and we've got some flux here, and that flux is changing with time. That's what we're saying right here. Okay, and so one way that could happen is if the velocity increased with time, or I guess if the mass increases with time. But I think conceptually it's easier just to think of the velocity increasing. So if we've got the velocity set up like this, and then it increases, to a longer vector there, then what'll happen is there'll be a compressive stress that results from that increase in velocity. Just intuitively, I think that makes sense. So for a positive diffusive flux, that's going to equal a positive change in momentum with time, and that's going to, if that's positive, then that's going to equal compressive stress. Okay, we saw that based on units it has to be a stress, and now we're going to use this to infer that it's compression. Okay, so now we need to take a look at the sign convention, because stress we can have positive or negative, and so the sign convention that we'll be using is that compression is negative and tension is positive. So compression we can think of schematically as like that. So compression works like pressure, and tension is going to be like that. Okay, so what that means is that a positive diffusive flux is equal to a negative stress. Compression is negative. Okay, so stress is a tensor, but we're going to, and we'll look at that in more detail, but for right now, I'm just going to use this sigma to indicate the stress tensor. And so we can say then that the diffusion, the diffusive flux of momentum is going to be equivalent to a negative stress. Okay, now the next term is the source. This is going to be the source of momentum that occurs internally within the control volume. So to get a sense for how that could work, we're having our this dependent variable c, the momentum per unit volume, that's being produced within the control volume. So the rate at which it's being produced is the source. So we have this. And we can think about that like this. Applied to C is rho and V. Okay, we think of it like that. And if rho is constant, then the rho comes out and we have that. Okay, well, this term, let me just make sure we keep things straight here. So this term, dv dt, that is acceleration, the rate of change of velocity with time. So this is going to be rho times acceleration. And so the source of momentum is the density times acceleration. Well, one source of acceleration could be g. So that's the gravity acceleration. So we can say, well, rho a, one case of that would be equal to g times rho g. Let's write it as rho g. Okay, where this is just a generic acceleration, but we're saying, well, let's consider it specifically gravity, the gravitational acceleration. We can write it as a vector because it has a particular direction. It's causing this acceleration downward. And we can also write that as just the rho g. Usually we think of that as just the unit weight of the fluid. So unit weight. Okay, so that's a case of a source of momentum that occurs within the control volume. It's just produced within the control volume as a result of gravitational acceleration. Now, what I'm going to write in the notes is that this we'll just call F to be a body force. That's a force that occurs within the volume. Sometimes you'll see it written as a volume force. But at least one example of this would be the unit weight. And unit weight is then this body force that's going to create, that's a source of the hydrostatic pressure. Okay, so we'll say the source will represent as F. And we'll think about it in terms of the unit weight as one case. There are going to be other potential sources of momentum, but this will be the most common one. Okay, so with all of that, we can summarize it and come back here to our conservation equation. And we can say that the governing equation is the divergence of the flux, which we can write as an advective term, and this diffusive term that we saw as minus sigma, and then the rate of change of storage is that, and that equals force. Okay, so there is at least this first cut through the conservation of momentum. Okay, so what I want to do now is simplify that momentum balance a little bit. And we could use it in this form, but as it turns out, this is a little awkward to deal with. And so we're gonna fiddle around with that and get it into a little bit of a simpler form. And so the first thing that I'm going to do is I have this form because it follows right from that. That term is this one, and there's the storage, and there's the source. But what I want to do is get this to end up being the form that is used by Comsol. And so to do that, I'm going to just rearrange some things, and let me explain what I'm going to do. So this thing here, this nabla operator, it operates on both of these things. So I can distribute that and have it operate on just this one, and then I would have another term like that would result from this minus that. So what I'm going to do is I'll do that out, and then this term here goes over on this side, and this term here goes over on the other side, and this term comes over here. So I'm going to switch it around, and we end up with that. So this thing is the same as that. I've just put terms on different sides. And again, that's just going to be to set us up so that we get the same form that we'll see in Comsol. All right, now we need to simplify this term a little bit. And what we're going to do is use an identity that says this. So here's this nabla operator applied to two vectors that are multiplied together. And that identity looks like this. So this is kind of like the product rule, except it's for these two vectors that are multiplied together. Usually, you think of the product rule as just two two scalar variables, but for the product rule, it looks like this. Okay, so you would apply the nabla operator just to that term, like that, and then you would apply it to the second term, and you end up with a form that looks like that. Okay, so for our case, U is the mass. This is like a mass flux, and V is a velocity. So if you have a velocity and you multiply by density, then the velocity has units of length per time, and the density has got units of mass per volume. So you end up with mass per area per time, which is a mass flux. Okay, it's also a vector. So we can just substitute in, and when we do that, we get that this thing is equal to okay, like that. Now, what we're going to end up doing is using this term here. The nabla is we're gonna interpret this to work like this. The V is dotted into, the velocity is dotted into the nabla operator, and that'll create another operator that will then be applied to that velocity. Okay, so that's the way we'll interpret that thing. And so that's going to allow us to simplify things down a bit. If we start with the left-hand side, from that version there, and then we have the next term is this term with the two products, which I'm expanding out here. So I get this. And I'm not writing the arrow over the top of them. These are vectors, but I just I guess I'm getting a little bit lazy. But like all the V's are vectors. Okay, so there's this term, this expression written out where we've included this. Now, what we're going to do is take another step, and that we can just write out as the product rule, where this is a vector times a scalar. So that's this. Okay, so what I'm going to do now is take that term and group them together. So I'm going to rewrite all this stuff. And this term and this term, see that V, there's a V there that I can pull out. And then I've got that. So that's this, and then I've got these next two terms, which is going to be like that. Okay, and so now this is kind of a clever little trick because this thing right here, we group those terms, and so let me go back. I'm gonna go back. This is this is just a PowerPoint slide here, so should be able to go back. Come on. Hmm. Okay. So let's see. Go back. Let's go back to this conservation of mass, right? So this is what we ended up with for conservation of mass. And let's say if there's no source, then that's zero. Okay, so what this says is for conservation of mass, the divergence of that thing, that's the mass flux, plus the rate of change of the density is equal to zero. Okay, that's what conservation of mass means if there's no source. So here's what we can do. I guess I got to go do it like that. Okay, so there it is. That's the term. That's conservation of mass. And if we're conserving mass, that's zero. Okay, so that means that we now have this. And all that stuff is zero, and now we just have and I think maybe I'm going to write that little hats on there to show that they're vectors. Okay, so now this is also conservation of momentum, but we've simplified it down, and we've got the main thing that we did here. If we look back at where we started, we've simplified things by expanding that term and expanding that and just getting it into a little bit of a simpler form. This thing becomes that, and this thing becomes that. And now we're ready to continue. Okay, so that's conservation of momentum, at least so far. So now what we have to do is, I say up here it's a detour. So we're going to take a bit of a detour and look at what will be called the constitutive equation for Newtonian fluid. So if we go back, this term right here, that's the stresses in the fluid. And the stresses that occur in the fluid are going to depend on how the fluid behaves. And the description of how the fluid behaves is given by the constitutive equation. So the simplest kind of fluid that we can deal with at this point is called a Newtonian fluid, and we can think about that. Well, I guess in general we could think about stresses in fluid like this. So if we've got a stress in a fluid, we could describe that like this, where P, this is the average stress, and we could take the normal stresses in the three directions and add them up and divide by 3, and then that's the deviation from the average stress. Okay, so and the minus sign is because of the convention where stresses, a positive stress is considered a tension and a negative stress is considered a compression. A positive pressure is a compression. So we have that minus sign to reconcile the sign convention. Okay, so and this is, I mean, I think this is pretty intuitive that we could say we wanted to set things up like that, where the stress is just equal to an average plus a variation from the average. And now the constitutive law is going to be this. So there's the pressure. Pressure is going to be the mean stress. And the variation, we're going to do, we're going to write it like that, where u is the velocity, and we have the we're gonna take this as the sum of these two velocity gradients. So the stress xx, sigma xx, is going to be the gradient of the velocity in the x direction, which is u, taken in the x direction, and that's the same thing. So we're going to take those two and add them together, and that'll just be 2 times that velocity gradient, okay, multiplied by the dynamic viscosity. And so we're going to say that that is the normal stress, the variation in the normal stress compared to the pressure. Okay, and we'll do that. We're going to set it up in this form because we're going to say that the shear stress is also defined in terms of velocity gradients. And so sigma xy is going to be equal to this proportionality, the dynamic viscosity, and then gu dy. So, if we have something like this, coordinate system like that, there's x and y. U is in that direction, and v is in that direction. So if we have a velocity that goes like this, this is u going in that direction, and the du dy is how that velocity changes in the y direction. So it would be like that slope. And we're also going to add to that dv dx. Okay, so v that's the velocity component in the y direction, and so that's going to be like that, and that may well change in the x direction. So that slope would be dv dx. So the shear stress that we're going to call sigma xy is the sum of these two velocity gradients times the viscosity. Okay, and well, you can see also that if we had dyx, then we would just flip these, but this would be dv dx, and this would be du dy, and there would be the same. So these two are the same. We have other terms here. This is sigma xz, and in that case we take the derivative of the velocity in the x direction with respect to z, and the derivative, and that's the velocity in the z direction with respect to x. Okay, so that's another shear term, and then we also have yz. Okay, so these are what we mean by, or these are how we're going to determine the stresses in the fluid. So sometimes you'll see these things written with sigmas, and sometimes that also is written with a tau. And so this then gives rise to the stress tensor, which I show over here. And this is a version where the normal stresses are with sigmas and the shear stresses are shown with taus. Okay, so and also I'm using index notation. So we might have x be the first index and y be the second index. So this would be the same as tau xy, and that's also could be denoted as sigma xy. And then this would be sigma yx. And what we said over here was that those two are the same. So it's a symmetric tensor where these terms are the same. And so in order to uniquely define it, we have to have the normal stresses and then these three shear stresses. Okay, so that's the constitutive law. That's how we're going to describe stresses in terms of velocity gradients. And we can then take this stuff that we wrote out here and we can write it in a more compact form like this, where we've got sigma ij with these indices. There's the pressure, and then here are these different gradients where we can substitute in the I and j and the j and I. Now this also is using this thing that's called the Kronecker delta, and this thing is going to equal, it equals 1 when I equals j, and it equals 0 when I does not equal j. So we put that Kronecker delta there so that when these two are equal, like when we have sigma xx, they're equal, that makes this equal to 1, and that gives us minus p plus mu times these gradients here. But when these are different, then this goes to 0. Okay, so that allows us to have this form here give us this form up here, where you can see for these shears that we don't have any pressure appearing there. Okay, so there's the constitutive law, and here I just rewrote it. We're still on a detour, so we've still got a little bit more filling around here to do. This is a velocity gradient and a different but related velocity gradient. Now, we saw last time that velocity gradients were related to the strain rate. So the strain rate in xx is this. It's 1/2. You add those two together and go divide by 1/2, and that just is going to give that back because these two are the same. And you would have a similar approach for the shear strain rate, where you would add these two together and divide by 2, in which case these two are different. So we can see then that the strain rate is related to these same velocity gradients that we were using. So we can write out a strain rate tensor. So there's the strain rate xx, and that equals that, and the strain rate yx is here, and zx is here, and so on. So these terms match up. There's epsilon dot yy is right there. So that's the strain rate tensor, and you can see that this is related to this. We just have that 1/2 term there. So if we take the strain rate and multiply by 2, we get this term in our constitutive law. Okay, so what that means is that this constitutive law we could also write like this, where 2 times the strain rate is giving us the same thing that we had there. Okay, so this ends up being just more compact way to write what we had here, and we got this from we had the expressions written out on the previous page. So hopefully that's clear where this came from and then where this came from. Okay, so this is a constitutive law for the stresses in a Newtonian fluid written in terms of the strain rate in the fluid. Now, Comsol uses this constitutive law, but they don't write it like this. They write it like that. Okay, and at first blush, the strain rate, it's not really quite clear that the strain rate is going to be equal to this. That's the Nabla operator applied to the velocity, and that's the transpose of it. Okay, so these are this thing here is the same as that. But let me just show you here real quick how that works. So here's the strain rate tensor, and this is what I just showed you. That is that, and that is that, and so on. Okay, so here is what Comsol uses, and let's look at this term first. So that means this. There's the Nabla operator, these partial derivatives, and there is the velocity vector. These are the three components of the velocity in the XYZ direction. Okay, so if we multiply these together, and this is multiplication now, it's not a dot product, but when we multiply these two together, we get this. So this U is, well, it's this ddx gets multiplied by or get applied to U, V, and W, and that gives us this row. There's the ddx's, the ddy's is there, U, V, W, ddz, U, V, W. Okay, so we get that matrix. All right, so that's what this thing means here. And if we take the transpose of that, then we're just going to swap these terms here and those two. So that du dy, that ends up there. And dv dx, that ends up there. Okay, so that's the transpose. Let me erase some of this stuff. Okay, so what I've got here is what that means and what that means. And now we're going to multiply by 1/2 and add these two together. So here's what you get when you do that. So here's 1/2 times this, which is that, and 1/2 times that. And then when we add these two together, it's this plus that, which is that, because these are the same. And then it's this times 1/2 plus that times 1/2, which gives us that. Okay? So this thing is the same as that. Okay, so this is an explanation for how that terminology is really this strain rate tensor that we've seen earlier. Okay, so now when we see this is that constitutive law for the Newtonian fluid. This is the strain rate, or that's 2 times the strain rate, and we can replace that with these, with this term here. Okay, so let's return from our detour. That's what it says we're doing here. We're returning from the detour, and when we left the detour, we had done this for the momentum, and during the detour, we have done that for the constitutive law. So this is going to go there, and I see actually what I've done is switch things around. So this is now coming over on this side, and this is coming over on that side. So I just swap sides. And again, I guess this is to get us in the right arrangement for what Comsol is using. So this is just directly substituting in the constitutive law, and then what we saw on the previous page, this thing right here, we can write like that, just a different format. Okay, so we now have these 5 terms. This applied to the pressure, and this applied to the strain rate, and the term F. Okay, so what I did now was essentially wrote what we ended up with on the last slide, but I took that. Now here, let me go back. So I just took I did this where if you take nabla and apply it to P is just a scalar. So this is going to give us minus del P, the pressure gradient. And then here it's going to be, if that mu comes out, we take it and dot it into these guys. Okay, so that's what that's going to end up being, and that's what we end up with here. Okay, so there's the pressure gradient, and there's this term, the divergence of this thing. Okay, so now these are what's called the Navier Stokes equations. If it's steady state, then the mass conservation just looks like this. Steady state with no fluid pressure source. And then the momentum conservation that we've been working on, it looks like this, and it's got these 5 different terms. And I wrote these 5 terms out here, where F, this is the body force, the unit weight. This del P, this is like the minus the pressure gradient. This term here is the shear stress term. This is viscous dissipation. So we're using up energy by shears that are dissipating energy in the flow. And then this term here, which is there, that's what's called the convective acceleration. And this is accounting for the energy that is used when we have streamlines coming together like that. So when the flow converges, it's going to accelerate just because of the pattern of the flow. And so if you trace a particle of water along this flow path, that particle is going to accelerate as it converges. I mean, you can think of this like this. Say we have a nozzle like this, and the flow is going along, and then it gets restricted in this nozzle. It's going to be the velocity in here is going to be faster than it is in here because it's converged and it has to now flow through a smaller area. And so a fluid particle, a little packet of fluid, is going to accelerate. It's going to feel this. It's going to be moving faster. It's going to accelerate, and so that's called convective acceleration. This term here, where you actually have the time derivative of the velocity, that's what we'll call unsteady acceleration, and that's just that's just how the fluid velocity is changing with time. So you could have convective acceleration, like what I'm showing right here. A little fluid packet is going to be speeding up along the flow path. That could happen even though the flow is steady. It doesn't change with time, but the fluid itself feels like it's accelerating because it goes faster as it moves along the flow path. Okay, so we've got these 5 different terms in the momentum conservation. And these are the Navier Stokes equations, and these are used to solve problems involving flow in open water. And if we take a look in Comsol and we use one of the physics modules that that does this kind of analysis of fluid flow, and we look at the equations that are given in it, here's what you see. This is, well, at least this is what was shown probably in version 5.3. I haven't checked the most recent version, but it'll be something very similar to this, if not identical. So on the left-hand side, these guys, the transient term for unsteady acceleration, convective acceleration, and then on the right side, we have, there's the pressure, minus pressure, and that I, that's the same thing as the Kronecker delta. And yeah, I guess we should probably have a Kronecker delta in there. Or this I, essentially it has the same form. And then this term here, which is what we have. And again, just a little bit different because they've pulled out this nabla operator, and then there's the unit weight. And this is the mass conservation. So that's mass, this is momentum. Okay, so that's how we get the various different terms in the governing equation that Comsol uses for incompressible flow. Now, another simplified version of this that is used for some applications where the flow is very slow is the Stokes equation. And if the flow is very slow, then if you take the time derivative, then it's going to be really small. So this is the rate of change of the velocity. So if it's very slow, then that's 0. And the convective, if the flow is slow, then you can kind of think of this as a velocity times a velocity. So if the velocity itself is very slow, then you multiply velocity times velocity, and that will be small. That'll be second order, and so that is just set to 0. Okay, so that gives you then this, where you've got a pressure gradient, and this term here that is doing the viscous dissipation. So that's like the friction. That's the head loss due to fluid flow, and then that's the body force. So this is Stokes equation, and this is useful for very slow flows. So in order to set up problems like this, we have to have two properties, the fluid density and the fluid viscosity. The volume, the force, this term F, we associated with the unit weight. And so the volume force is, it's included as, or the, this term F is included as a unit weight, and it is in some setups called a volume force, and it's going to be the unit weight, and then that term, that's del Z. What that does is it causes this force to be that thing equals 1 when the vector is pointing up, and it equals when the vector is pointed parallel to z, then this equals 1. Otherwise, it equals 0. So you could write out the vector like this, where that's the unit weight, rho g is the unit weight of the fluid, and this would be an XYZ format. So this is creating a volume force from the unit weight acting in the negative z direction. So that causes the that would create, for example, a hydrostatic pressure increase with z. So in order to solve these problems, we'll need to have boundary conditions. So the default boundary condition is that there's no slip along the wall. So the velocity um, perpendicular to the velocity at the wall is equal to 0. We could also specify the flows at the boundary, the flows normal to the boundaries. And one thing to keep in mind is that for steady state problems, we're going to need to specify the pressure somewhere. If you don't do that, then the problem you won't be able to solve the problem. So just keep that in mind. If you get some peculiar errors, uh, just check and make sure that you specified the pressure someplace. So these are the different conditions. You could specify the pressure on the boundary, um, or you could specify the velocity. So this is the normal velocity, and you could also specify velocity components. And in some cases, the velocity would be 0, and that would be a no flow condition, no flow perpendicular to the boundary. There's also this condition where the velocity itself is equal to 0. So that means that the velocity goes to 0 at the boundary. This is a little bit different. This means that the velocity perpendicular to the boundary is 0, but the velocity parallel to the boundary could be non-zero. So, if this is the boundary, you could have flow like this, parallel to the boundary, with that kind of a boundary condition. With this boundary condition, then the flow right there has to be equal to 0. The flow right there could be something, right? And it would increase as you get away from the boundary. But right at the boundary, the flow would equal to 0 for that case. So those are the different conditions. And then there are a variety of examples that we can take a look at, and we'll do that with exercises that we'll have for homework.